All right, so this is part two of using the qualitative perspective to determine acidity. So in the last video, I talked about how you have an acid and the base deprotonates that acid and you're left with the conjugate base. So now we're going to look at the conjugate base to determine how acidic that proton is that was taken off. And to do this, we use the acronym ARIO. So now we're going to go through a bunch of examples and look at ARIO in more depth. So A for atom. When you're looking at what atom is holding the negative charge of that conjugate base, you're looking at two things. You're looking at the electronegativity of that atom, and you're looking at the size of that atom. And so after an acid is deprotonated, you have that negative charge. You're not going to look at electronegativity and size at the same time. You're going to look at one or the other. And how to determine whether you're looking at the electronegativity or the size is based on the trends of the periodic table. So if you don't remember, electronegativity is going to increase going to the right, and it's going to increase going up. So we're going to leave electronegativity in red, and then we're going to look at size using blue. So let me change my pen color to blue. So then for size, it's going to be the opposite. So size is going to increase as you go down on the periodic table, and it's going to increase going to the left. So for example, fluorine here is very electronegative and it is very small. So back to red, you're going to look at an electronegativity of an atom if you're comparing two different atoms that are horizontal to each other on the periodic table. So for example, if you're looking at nitrogen versus oxygen, so say you're looking at a molecule and you have a proton on nitrogen and a proton on oxygen, and you want to know which one is more acidic. After you deprotonate both of those, you're left with a negative charge on a nitrogen and you're left with a negative charge on the oxygen. So, like I said, those are horizontal to each other on the periodic table, so you're going to use electronegativity to determine which one is more acidic. And so, as it says here, if you're more electronegative, you're more stable. Because remember, electronegativity is basically the affinity of that atom to hold electrons. So if it's very electronegative, it really wants those electrons close to it. So then for size, the bigger the atom is, the more stable it is. So this is going to be if we're looking at atoms that are vertical to each other. So say we're comparing two different protons and one is on sulfur and one is on oxygen. If you look at the periodic table, those are up and down from each other, or they're vertical to each other. So that is when you're going to be looking at the size of the molecule, or sorry, the size of the atom that it's on. So here is a good example of this. This is actually using the same elements that we did in the last slide, but I think this will give a little more clarity. So if you deprotonate an oxygen and you deprotonate a nitrogen, you're left with an extra lone pair on these and a negative charge. So now you say, okay, which one is more acidic? You're going to go back to the periodic table. You see that nitrogen and oxygen are horizontal to each other, so you're going to look at the electronegativities. Oxygen is more electronegative than nitrogen, so the oxygen is going to hold the more acidic proton. So second example, same question, but it's talking about different compounds. So which compound is more acidic? Here you have hydrogen sulfide and you have water, which are essentially the same molecule, but you're exchanging an oxygen for a sulfur or other way around. So if I deprotonate both of these, you're left with a negative charge and an extra lone pair. So lone pair here, lone pair here. So you're comparing sulfur and oxygen. So back to the periodic table, sulfur and oxygen are vertical to each other. They're up and down from each other. So you're going to say, okay, which one is bigger. And looking at the trend, you know that as you go down on the periodic table, you get bigger. So sulfur here is going to be the winner, and it is going to hold the more acidic proton. So this compound is going to be more acidic. Now we're going to look at resonance. So remember I said that ARIO is in the same order of importance. So say we deprotonate ethanol, we're left with 3 lone pairs on this oxygen. It originally had 2, and then once we deprotonate, that hydrogen donates its electrons back to that oxygen and a negative charge. And same thing here. That hydrogen is on an oxygen. So once we deprotonate it, you take away that hydrogen and it donates its electrons back. You can't use A because they're both on oxygen. Oxygen has the same electronegativity and size as oxygen. So the next thing we look at is resonance. If you look at ethanol, this negative charge is localized on this oxygen. These lone pairs can't be pushed anywhere, but for acetic acid, it can. You have another oxygen with a double bond right here. So if we push these electrons here, and then we push these electrons up, you have a resonance structure. And I'm not going to draw all of the lone pairs, but you know they're there because of that oxygen. So then you're left now with a resonance structure. I'll go ahead and draw this out. So now this negative charge is delocalized from this oxygen and it can be moved throughout the molecule. So the more resonance it has, the more stable that negative charge is. So acetic acid here is going to be more acidic. Now we're going to look at induction. Here we have a proton on oxygen. Now we're going to look at resonance for both of these. Once you deprotonate it and you're left with a negative charge, you can move it throughout the atom because it has resonance. Throughout the molecule. Same thing here. It has the same resonance, and this is super important, it has the same amount of resonance. If you have 2 molecules with resonance, but one can produce more resonance structures than another, then that one is also going to be more acidic because it has more resonance. But in this case, they both only have one other resonance structure. So now we're going to look at induction. Remember from the last video, I said induction is the presence of electron withdrawing groups that are going to try to suck up that electron density. So over here, we just have a carbon right here, nothing special. But on this molecule, you have 3 chlorine atoms right here. And remember, chlorine is very electronegative. So it is essentially going to want to suck up all of this electron density right here. And then another thing to note is that, say for some reason you have 2 chlorine atoms on this molecule over here. So everything is the same, they both have induction, but still this molecule right here has 3 chlorine atoms. So the presence of more electron withdrawing groups is going to make it more acidic. So I put down here, with the addition of a chlorine, the compound becomes more acidic. Last thing we have is O for orbital. So in the last video, I talked about the trend. So the most stable here is going to be sp hybridized orbitals, and then in the middle sp2 and then sp3. And so this can be kind of confusing, but I have a little way that I like to remember this, and I think it really helps. So remember that you have a nucleus and it has all of these positive protons in the nucleus, and then the s orbital is the closest to the nucleus. So remember, orbitals hold electrons, so the s orbital is going to hold the electrons that are closest to the nucleus, and electrons are negatively charged, and this nucleus right here has all of the positive protons. So then you have all of the different p orbitals, which I'm not going to draw out because that takes a lot of time, but those are going to be a little further away than this s orbital right here. So essentially, since the s orbital is physically closer to the nucleus and it holds those negative electrons, that nucleus is going to attract those electrons more, because remember, positive attracts negative. So if you have an sp hybridized orbital, I like to think of it in a ratio. So you have one portion of S character to one portion of P character. So the more S character you have relative to P character, the more stable it's going to be, because that positive nucleus is going to hold those negative electrons more tightly. So then over here you have one portion of S character, and this is sp2. So that's going to be two portions of P character. So it's going to have more P character, and P character is further away from the nucleus, which is not as stable. Same thing over here, you have one portion of S character to three portions of P character. So the reason that sp hybridized orbitals are more stable is because they are physically closer to the nucleus, because they have more S character. So looking at this, it's asking what protons are more acidic. Say we deprotonate this carbon here, you're left with a lone pair and a negative charge. And then if we deprotonate, if we deprotonate this atom here, you're left with a lone pair, negative charge. But remember, you have the hidden atoms. So this carbon originally had two atoms, but then we deprotonated. So it's left with one hydrogen. And then this one originally had three protons, but we deprotonated it. So now it's left with two hydrogens. So now if we're looking at the orbitals of both of these, you have 1, 2, 3 electron groups on it. So it is going to be sp2 hybridized. And then if you look at this one, you have 1, 2, 3, 4 electron groups on this carbon. So it is going to be sp3 hybridized. So this carbon right here is going to be more acidic because it has more S character.
I hope you found this video to be really helpful. The concepts and information presented in these videos will be true no matter what Organic Chemistry 1 class you are taking. However, the concepts presented in this video are referencing material currently covered in Baylor University's coursework. Remember, if you are a currently enrolled Baylor student, we offer free tutoring services. Our tutoring center is located on the first floor of the Sid Richardson building. You will find all the details you need about these services on our website, www.baylor.edu/tutoring. You may schedule a free 30-minute one-on-one tutoring session online, or just drop in during any of our open business hours. For more information about our current services, please visit our website. Thank you.